Good afternoon, everybody. First of all, I must thank the Professor Roy of this campus. You know that I am from BITS Goa campus, so I am a part of this system. So, but my visit was long due to various reasons. I wasn't able to come. So it was a very it's a pleasant experience for me to seeing that how the BITS Hyderabad campus is right now, and also to the organizers of this conference, our delegates from France. So today, what I'm going to discuss with you is the some of the work what we are doing for the last 2-3 years in my lab. So here, actually, with our current goal of the United Nations, that SDG 6, that the ensure the clean availability of clean water, and SDG 7, the affordable, reliable, sustainable energy. One of our main objectives. So the work we are doing in our lab is the developing different types of material. Basically, we are synthetic material chemists, but we are also keeping in mind how the materials with various structures, shapes, composition, how we can make them useful for various applications. So when we are choosing our target material, we are keeping these things in our mind that we are targeting material should be useful for these applications. So therefore, we are the materials we are developing, that some of them they are useful for the photocatalysis, some of them are useful for the electrocatalysis, some photoelectrocatalysis. Also, we have developed some multifunctional material which is good for as a cathode material for supercapacitor applications, and as well as they show good good electrocatalytic property for water spilling, particularly for OER reaction. So these are some of the examples of the material we are developing for the last couple of years. So from them I will take 2-3 examples which I will just present to you. So here a couple of representative structures. I am scanning electron microscopic pictures. So particularly for the students who are present here, I know that the senior researchers, we are well known about this, they know it, but for the students they should know that this is the 2D material like reduced graphene oxide. You can see that some of the layers are very thin, optically transparent. This is the porous carbon. We have we have prepared this porous carbon from coconut fiber. As Goa, there are lots of coconuts are available. We are having that graphitic carbon nitride. You know that the graphene is like C6H6. Now, if you can replace this this benzene ring, that 3 alternative carbon by nitrogen, it would be the graphitic carbon nitride, and it is a very layered structure. It is having a semiconducting property where the graphene is zero band gap material. So exploiting these, which we are trying to see how we can use this material as a photocatalytic support, and their optoelectronic properties, how we can to make the catalyst. Here it is almost a brand new material, but right now it's a very hot material. In the Drexel University, Professor Yuri Gogotsi in 2011, he was synthesized. It is the layered structure of titanium carbide, and though we are calling it titanium carbide, its surface is also functionalized by some terminal groups like oxygen, fluorine, OH minus, and depending upon how you are playing with these functional groups, with their with the space and all this, and how you can, what are the aims? There are several hundreds are amexins are possible. The very popular method to make the amexin is that from the max phase, which is titanium aluminum carbide, and by an etching process you remove the aluminum layer, so you can get the titanium carbon layered structure. And now it is up to you whether how you can doing some intercalation process, how you can monitor the play with the layered structure, whether you are doing to exfoliation. But it is the method I am just told, it is one of the most popular technique, but there are several other techniques also available to make this amazing, and this titanium Ti3C2 is one of the popular examples. This there are several molybdenum, niobidium, all are there. Theoretically some exist, some of them they are yet to synthesize, but it is there. Now we have developed some nanomaterials with some exotic structure, like copper sulfur sulfide with dendritic structure. We have made some manganese ferrite. It is having a magnetic property, and you can see that there is a broken sphere, which shows that it is the hollow sphere. We are having the bead-like structure of silver nickel alloy. We are having the manganese cobalt layer double hydroxides with a needle-like structure. They are just randomly arranged with each other. We are having some spherical very nanoparticle of cobalt ferrite. Again we are having cobalt nickel structure. These are the with the dendrimeric structure, and we have developed these methods to synthesize it, because all of this material, they can be prepared in different morphologies, and depending upon the morphology, how their properties, which is useful to you, that can be varied. Like suppose you are doing some, you are aiming for some doing some charge transfer reaction. There, if you can make some the needle-like material, there could be a possibility that the charge transfer can happen in a ballistic transfer method, and it becomes very efficient. So you have to judge that what type of material you have to make, what could be its composition, what could be its morphology. So you have to either develop or judiciously chosen your synthesis methodology. Here I am giving you an example of a nanocomposite composed of cadmium sulfide, graphitic carbonitride. Cadmium sulfide is a very well-known photocatalyst, and we have made a composite with graphitic carbonitride, which is also a semiconducting material, and we have using this catalyst. No, there is another catalyst we have made, which is the cobalt ferrite and RGO. Using that catalyst, we have made a photocatalyst, which and using that we have made a prototype where it is a solar cell, and we got some wastewater, which is from a textile industry, and we processed it through this, and we got a clean water. I must say, when I am talking about clean water, it is not drinkable water. I am not saying that. Okay. So, and thus it is a prototype, in the lab scale prototype, I would say. So now we have also tried to explain the photocatalytic property of the catalyst, what we have synthesized, what kind of mechanism it follows. Because when we are trying to develop, or we are designing to develop a photocatalysis, couple of things you need to keep in your mind. First of all, though you know that titanium dioxide TiO2 with band gap 3.2 EV, it is not very good for the for the visible light. You need the UV light, okay? Because to the generation of electron, the charges like holes and photogenerated electrons. So our nowadays our main sole purpose is that to make the photocatalysts which are active in the solar light irradiation. That is one thing. Second thing, so you have to see that how their optoelectronic property is in the solar light, how much a broad range they are absorbing. You have to see that there is another situation is happened. So you can say that, sir, when the band gap energy, if we can take a material with a very small band gap, it will be easy. You need a radiation with a small frequency, and you can get a easy band gap. But what will happen that when in these cases, when the electron and holes are generated, they recombine. So you cannot see their photocatalytic activity. So the band gap engineering is also a very critical parameter. Then another thing is another thing what we have to keep in mind, that how the charge transfer things are happening. So keeping all these things in mind, first I would like to tell you that what kind of photocatalysis we have prepared. It is the cobalt ferrite graphitic carbon nitride. First, to understand its photocatalytic activity, initially we have treated it, which we have evaluated its photocatalytic activity with some model catalyst at methyl orange with and methylene blue, rhodamine B, like that, and then we collected some dye which are used in textile industry, the real dye, and we made the solution and see that what kind of photocatalytic activity we can see. Here the material we have used, it is the cobalt ferrite graphitic carbon nitride. Cobalt ferrite is a semiconducting material. Graphitic carbon nitride is also a semiconducting material. So we have done by that how we did some band gap engineering. Not only that, here you must see that cobalt ferrite is a magnetic material. So after doing the photocatalytic reaction, you can see that this colored has become colorless, and if you can put a magnet there, the catalyst can easily get gathered here. However, one more thing, whatever I am discussing, it is in the lab scale demonstration, in the pure academic work. No, I mean, people should not have any misconception that we have a long way to go, but generation of the knowledge is also very important for us. So here you can see that we have done the traditional X-ray diffraction, scanning electrons, FEHM study, the morphology, and you can see that this graphitic carbon nitride, the nanoparticles are decorated on the surface of this, and some of them have gone inside, so that the layered structure of graphitic carbon remain maintained. Because one of the issues, the layered structure material, 2D material, they face is that after running couple of catalytic cycle, their structure they collapse. So maintaining the layered structure is also very important, where we can these nanoparticles can act as a spacer in between the layers. And we have done the solid state UV DRS spectroscopy. We have seen that, if you see that this red color is the graphitic carbon nitride, but when we have added the cobalt ferrite, it has become a long range absorption is happening, where the graphitic carbon nitride is having a 2.7 electron volt band gap, but by addition of some amount of cobalt ferrite, it has reduced to 1.04 or something like that. No, sorry, cobalt ferrite is 1.04, so it has become 1.4. So then we have done the photocatalytic activity under solar light simulation, under simulated solar light radiation, and we have did in a very simple way, the traditional way to monitor its kinetics. We have seen that when the lambda max value is almost 0, we can consider that the reaction is complete. And here we can see that for different dyes, the like methylene blue, methyl orange, that it is around 35 minutes, 40 minutes, 90 minutes is happening, which is not that bad as far as the literature value is concerned. Now we have added how to understand how the reaction mechanism is happening. We know that it goes by radical, some radical generates OH dot, O2 minus dot, some H plus also can generate, and they are responsible. But which one is more dominant? See, all of us, we don't might not have the EPR machine instrument, so there is a very simple method to capture that, that you have to have some scavengers. If you add those scavengers, and for different chemicals are there for different radicals. So if one radical, say OH dot, is responsible for a degradation reaction. Now if you can scavenge it, what will happen? The reaction will be prolonged. So that way we can find out, and we have seen that we have added with the benzoquinone, which is the O2 minus scavenger for 2 minus, disodium EDTA for holes, isopropanol for OH dot, and we have seen that this OH dot is more more responsible for this. And so here now, based on these results, there is one, we have tried to explain the mechanism which is known as by S scheme mechanism. There are different schemes are there, like type 1, type 2, S scheme, Z scheme, and all this. So here, when the two semiconducting material, they are come before contact, that there, and then after, when they are coming in contact, then they adjust their Fermi level, and there is a one electron deficient center at the interface generates, and one is electron rich center it generates. Then when this the junction is exposed by the solar light, there the holes and electrons they generate, and here the electrons and the holes they combine with each other, but here the strong reducing electrons are there and remain, and the strong H plus remains, and they generate the OH minus, OH dot, and here we have used some one sacrificial agent H2O2, which is very cheap, which is environment friendly also. So that's how we explained our method. So here these are some textile dyes, and after treatment it becomes like this. So you also have to understand that when we are wearing this kind of very bright color clothes, at least 20 to 15 to 20% the dyes, they goes to the water stream, and they are they are sometimes they are carcinogenic also. Not only that, also they hamper the water life in the water body. Sir, how much time do we have? Do I have
5 minutes.
5 minutes. Okay, so we have made one more catalyst, which is the porous carbon. We have and there we decorated the copper and copper nanoparticle and cobalt ferrite. Here we have through FESM study, we have seen that how the pores are generated. These are the the coconut fiber, and now here you can see that the nanoparticles are decorated. We have done here we have taken some standard antibiotics, because antibiotics also considered as a pollutant, because antibiotic resistance is also a problem nowadays. So we have seen that, and then when we have mixed the catalyst with this antibiotic and expose it by the microwave, here we see that within a minute the decomposition is happening. But decomposing to what? All of them are going to carbon dioxide, water, and all this? Most probably not. So that's why after decomposition we have done LCM study and tried to identify what are the intermediates form, what are the small molecules form, and we are yet to evaluate that whether the toxicity of these small molecules. So here the mechanism is very simple, that cold ferrite, which is a magnetic material as well as a dielectric material. So when it is exposed by the microwave, it gives the magnetic loss as well as the dielectric loss, and it is a very good microwave absorber. So when it is microwave absorbing, that the absorbed microwave, it generates the temperature spots, hot spots there, and this porous carbon, it can host the nanoparticles, and here when this interaction between microwave and the carbon material, it also generates some hot spots, and when these hot spots are generated, that gives some energy to jump to do the generation of H plus and E minus. And here, if you see that this is the sort of the porous carbon, and sort of a semiconducting particle, and here this is another semiconducting material which is cobalt ferrite here, and in the interface there is a highly conducting copper is there. So where the generation of charge separation is happening, the electron through this, it combines with this, so it left here H plus here and E minus here, where the reactions happen. So I am quickly and also we have used this it is a multifunctional catalyst. Here we have also done the hydrogenation reactions using a, first we started with a very standard technique, very well known, that reduction of 4-nitrophenol to 4-aminophenol, and then we have done several nitro benzene compounds and evaluate its property, and we have also it's a very standard the mechanism is there. It's a 6 electrons transfer process, and there are this reaction follows through these intermediates. And here we are I'm just quickly going through that. We are made a catalyst composed of amexine and copper sulfide, and it is used as a electrode material, cathodic material for supercapacitor, and you can see that we have demonstrated its ability by lighting a couple of LED lights together. These are the FESM and ACM. Yesterday, Professor Roy has explained this oxygen generation OER method. We have done the standard electrochemical states, and like LSB, and we have studied the over potential, and we have calculated the Tappel slope. We have done the TOF stability test, etc. And we have seen that this material is a very good OER, particularly when there are iridium oxide and all this. They are the very costly, but they are the benchmarking material for the OER. So these are the couple of results I am trying to present with in front of you, and I am very much thankful to my funding agencies, and also obviously to my students who have really worked in the lab, and thank you all for listening me.
Thank you, Professor Ghose. I'm sure it's very interesting work which we are doing on photocatalysis, and I'm sure there will be a lot of questions, particularly from students, because instead of normal TiO2, you have worked on new materials and very good results on decolorations and things like that. And you, as you rightly said, that these are laboratory results, so we need to scale it up. So we can invite one or two questions if somebody has. If no one has question, I have one question. Along with photocatalyst, you are using H2O2 also.
Pardon? As a sacrificial agent.
So what it is sacrificing?
It decomposes and it produces the OH.
But that means it is oxidation using H2O2.
Yeah.
So how do you separate photocatalysis with H2O2? Because
No, this,
H2O2 also can, because it's a bleaching agent. You know, in textile
I know,
industry,
yeah.
people use a lot of hydrogen peroxide.
But sir, when it is exposed by the light, H2O2, you know that also very unstable. It readily forms OH dot. So that's why we have seen that the reaction without H2O2 with H2O2, how it is affecting.
How much is the difference?
It is affecting significantly.
Very good. Because normally, you see, I also worked on this, and then people ask for the cost, particularly in textile industry.
Yeah.
So as soon as you say that, yeah, I'm adding something else, people will say, okay, we will see later.
Yeah.
So-
And nowadays that ZLDI is also coming, zero liquid discharge technology is also coming.
Yeah.
So our thing is that it will not be it will be a tertiary stage.
I mean, I'm working with the industry, so I just want to give a hint. People ask how much it will cost per meter cube.
Not only textiles, are in every industry.
Yeah. So, friends, it was very good presentation. So, let us felicitate Professor Ghose.
Thank you, sir.
Long live India and France friendship.